Welcome to Electrochemistry with Ms. Taylor. Today we are looking at a released AP test question that actually features both electrolytic cell and a voltaic cell. So the first part we are given a balanced chemical equation, and we are told it's an electrolytic cell and it produces 235 grams of aluminum. So the very first thing they want you to do is to calculate the number of moles of electrons that must be transferred in the cell to produce 235 grams of aluminum liquid. So before I just jump into this, I'm going to plan out what I'm going to be converting. So I'm starting from 235 grams of aluminum. As always, you can convert grams to moles. And then we can convert moles of aluminum to moles of electrons. How, you say? Well, we know the charge of an aluminum ion, that it's going to go to aluminum with a positive 3 charge. Okay, so when we write this out, it looks like this. 235 grams of aluminum. And then we use molar mass, so 1 mole of aluminum has a mass of 26.98 grams. And then for every 1 mole of our aluminum ion, and I can make this leap because electrons don't contribute to mass, we have 3 moles of electrons. So punch that into your calculator, and I'm going to round that to 3 sig figs. So you should get 26.1 moles of electrons. Moving on to part B. Now they're going to tell us that they used a current of 152 amps to do this, and they want to know how long it took. Okay, one of the big things that you need to remember, an ampere, which is what they're shortening to amp, is the same thing as the number of coulombs per second. And you can use that as a conversion factor. So when we set this one up, I'm going to give you my plan of attack. I'm going to start from that mass of aluminum again. So from 235 grams of aluminum. And it's going to look much like the previous one, because I'm going to convert that to moles of aluminum and then moles of electrons. But then my next step is going to be to use Faraday's constant to convert moles of electrons to coulombs of charge, and then use the amps to get to seconds. So the hold there's my molar mass like I had used previously. And then for every mole of aluminum ion, we get 3 moles of electrons. And then Faraday's constant, which is something that's listed on the equation sheet given to you at the AP test, says there's 96,485 coulombs of charge per mole of electrons. And then our current was 152 amps, or 152 coulombs per second. So we need the coulomb on bottom. So I'm going to put 152 coulombs on bottom and 1 second on top. So punch that one into your calculator and round that to 3 significant figures. You should get 16,600 seconds, which is a good while. Now we're going to move on to part C, where they like to throw in a gas law. Why do they do that? Well, because free response questions on the AP test tend to have cross-topic calculations. Just does. And in this case, if you go back to look at the original equation, there was carbon dioxide gas produced. So in order to get the volume, this is not at standard temperature and pressure, we're going to have to use the ideal gas law, PV equals nRT. And we have been given the temperature, we've been given the pressure, we are looking for volume, and we can figure out the value of R from our equation sheet, but we don't have the number of moles. That's where we're going to have to use stoichiometry to go from the mass of aluminum to the number of moles of carbon dioxide. So, going back to the fact that we have 235 grams of aluminum formed, I'm going to convert that to moles. And then to go from moles of aluminum to moles of carbon dioxide, we need the mole ratio from the balanced chemical equation. So I'm going to scroll back up so we can look at that. So there are 4 moles of aluminum to 3 moles of carbon dioxide. So 4 moles of aluminum on bottom, 3 moles of carbon dioxide on top. Punch that one into your calculator, and I'm going to carry this out a bit because this is an intermediate calculation. 6.5326 moles of carbon dioxide. Then I'm going to plug into the ideal gas law. So 0.962 atmospheres times the volume equals 6.5326 moles times the value of R. Remember, the value of R depends upon the unit used for pressure. So we're going to need the R that uses atmospheres, and that one is 0.0821. And the unit for that is actually liter atmosphere per mole Kelvin. And then they were nice to us and gave us our temperature in Kelvin, so we don't have to convert it. And do a little bit of algebra, round that to 3 significant figures. You should get 168 liters of carbon dioxide gas. Moving on to part D, and I can't type in subscripts. The Al2O3 must be in the liquid state rather than the solid state. Explain. Okay? In order for charges to move, okay, or for electricity to be conducted, ions must be mobile. So, electrolytes have mobile ions. If something is solid, non-mobile ions. If it's liquid, there are mobile ions. And mobile ions can move charges, which means they can conduct electricity. So, molten ionic compounds are capable of conducting, as well as when they are dissolved in water. However, when they're in their solid state, no dice. Scrolling down, so here's where we switch gears to the voltaic or galvanic cell. And on this one, they tell you that they're putting aluminum into some concentrated potassium hydroxide, and the following occurs. Now, they don't want you to figure out if it will occur. They're telling you that it's going to happen. Okay? So, that means that this should be a thermodynamically favored reaction, which means we should get a positive E cell and a negative delta G. Okay? So, scrolling down just a little bit. So the first thing they want us to use is to use this little piece of reduction potential table they gave us to figure out what is the cell potential in volts for the formation of hydrogen gas at 25 degrees Celsius, which is standard conditions. And hydrogen gas is formed in this. So we have to figure out which half is oxidation and which half is reduction. So let's go to our equation. Okay. So we have water forming hydrogen gas. So in this case it's gaining. So this is our reduction half. And if you look up here, the opposite of this one happens. This is written as a reduction, but the opposite happens. So this is our oxidation half. So the reverse happens, and that also means that we need to change this to a positive. So now when we calculate our E cell value, we're going to add the reduction value to the oxidation value, because you can't have one without the other. And so we've got negative 0.83 plus positive 2.35, which is going to give you 1.52 volts. Now the second part of this question, I forgot to write in that this is what you're looking for. So they want you to find the free energy in kilojoules per mole of reaction for the formation, blah, blah, blah. Basically, they're saying use the same equation. So this is where you're going to plug and chug into an equation. They don't give you the E cell equation on your formula sheet, but they do give you this one. That delta G equals negative N times F times E cell. They don't put cell, they just put that, but you're supposed to know what that is. So, plug it in. Now, the N, that is moles of electrons. So, in order to figure that out, we're going to have to go back up here to this equation. Notice your balanced chemical equation does not feature any electrons, so we've got to go back to our half reactions. We've got one with 3 electrons and one with 2 electrons. So if we were trying to balance this to get that net-on equation, we would have had to multiply this half by 2 and that half by 3, which would have given us 6 moles of electrons on each side. So N is 6. F is just Faraday's constant, 96,485. And then we just calculated our E cell. So punch that one into your calculator, and then remember to divide by 1,000 because they asked for it in kilojoules. This is going to give it to you in joules. And so you should get negative 880 kilojoules per mole of reaction. Thanks for watching.